learning objectives. In this chapter, the user would learn the following aspects of raw material. Get introduced to multimeter, component tester, open resistor damaged. Get introduced to capacitor, piezoelectric diaphragms, piezo buzzers, spark probes and gaps, and transformers. Get introduced to batteries, cells and coils. Know about various potentiometer types, soldering techniques. Be familiar with optocouplers, piezoelectric transducers, and potentiometers. Multimeter. A multimeter or a multitester, also known as a VOM, volt-ohm meter, is an electronic measuring instrument that combines several measurement functions in one unit. A typical multimeter would include basic features such as the ability to measure voltage, current, and resistance. Analog multimeters use a microammeter whose pointer moves over a scale calibrated for all the different measurements that can be made. Digital multimeters, DMM, DVOM, display the measured value in numerals and may also display a bar of a length proportional to the quantity being measured. Digital multimeters are now far more common than analog ones, but analog multimeters are still preferable in some cases. A multimeter can be a handheld device used for basic fault finding and field service work, or a bench instrument which can measure to a very high degree of accuracy. Operations. A multimeter is a combination of a multi-range DC voltmeter, multi-range AC voltmeter, multi-range ammeter, and multi-range ohm meter. An unamplified analog multimeter combines a meter movement, range resistors, and switches. For an analog meter movement, DC voltage is measured with a series resistor connected between the meter movement and the circuit under test. A set of switches allows greater resistance to be inserted for higher voltage ranges. Amplified instruments simplify the design of the series and shunt resistor networks. The internal resistance of the coil is decoupled from the selection of the series and shunt range resistors. The series network becomes a voltage divider. Digital instruments use the same principles as analog instruments for range resistors. For resistance measurements, usually a small constant current is passed through the device under test and the digital multimeter. Quantity measured in multimeter. The following quantity can be measured by multimeters: voltage, alternating and direct in volts; current, alternating and direct in amperes. The frequency range for which AC measurements are accurate must be specified. Resistance in ohms, capacitance in farads, conductance in Siemens, decibels, duty cycle as a percentage, frequency in hertz, inductance in henries, temperature in degrees Celsius or Fahrenheit. Digital multimeters may also include circuits for continuity tester, sounds when a circuit conducts, diodes and transistors, battery checking for simple 1.5 volt and 9 volt batteries. Voltage meter. The voltmeter is used to measure the voltage potential across a component in an active circuit. It can be used to measure either DC or AC voltages. AC voltage can only measure sinusoidal, that is, sine waveforms. Ohm meter. The ohm meter is used to measure the resistance of a component. Power cannot be applied to the component being tested. The ohm meter actually applies a small voltage and uses Ohm's law to calculate the resistance from the measured current. Ammeter. The ammeter is used to measure the current through a component in an active circuit. It can be used to measure only DC current. Some multimeters can also measure AC current. Meter malfunctions. Check meter's battery. Review instructions to make sure all the meter settings are accurate for the type of testing being conducted. Check to see if test leads are broken or not connected properly. Inspect and test the fuse. Difference between multimeter and oscilloscope. Oscilloscope, graphical output is displayed. shows how a signal changes over time. Many only display voltage. Multimeter. Numerical output is displayed. Represents a complete signal with a single value. Measures voltage, current and resistance. Uses of multimeter. The multimeter is used as ohm meter, ammeter, measures AC or DC voltage. Electrolytic capacitor. An electrolytic capacitor is a capacitor that uses an electrolyte as one of its plates to achieve a larger capacitance per unit volume than other types. The large capacitance of electrolytic capacitors makes them particularly suitable for passing or bypassing low frequency signals and storing large amounts of energy. They are widely used in power supplies and interconnecting stages of amplifiers at audio frequencies. An electrolytic capacitor will generally have higher leakage current than a comparable capacitor and may have significant limitations in its operating temperature range, parasitic resistance, and inductance. Most electrolytic capacitors require that the voltage applied to one terminal, the anode. Non-polarized electrolytic capacitors are available for special purposes. Capacitance tolerance and stability, equivalent series resistance, ESR, and dissipation factor are significantly inferior to other types of capacitors. Leakage current is higher and working life is shorter. Capacitors can lose capacitance as they age and lose electrolyte, particularly at high temperatures. Construction. Aluminium electrolytic capacitors are constructed from two conducting aluminium foils, one of which is coated with an insulating oxide layer and a paper spacer soaked in electrolyte. The foil insulated by the oxide layer is the anode, while the liquid electrolyte and the second foil acts as the cathode. The two most popular geometries are axial leads coming from the center of each circular face of the cylinder, or two radial leads or lugs on one of the circular faces. Polarity. The aluminium electrolytic capacitors, the layer of insulating aluminium oxide on the surface of the aluminium plate, acts as the dielectric, and it is the thinness of this layer that allows for relatively high capacitance in a small volume. This oxide has a dielectric constant of 10, which is several times higher than most common polymer insulators. It can withstand an electric field strength. Types of capacitors. The types of capacitors are as follows: aluminium electrolytic capacitor, tantalum, solid aluminium electrolytic capacitor with organic semiconductor electrolyte. Difference between polar and non-polar capacitor. A non-polar capacitor is a type of capacitor that has no implicit polarity. It can be connected in either way of circuit. For example, mica, ceramic. A polar capacitor has an implicit polarity. It can be connected in only one way. For example, lead. Reliability and length of life. The capacitance falls off rapidly below room temperature, while dissipation factor can be 10 times higher at minus 25 degrees centigrade than at 25 degrees centigrade. Most of the limitations can be traced to the electrolyte. The electrolytes evaporate. Design life is most often rated in hours at a set temperature. Characteristics of capacitor. Capacitance drift. The capacitance of electrolytic capacitors drifts from the nominal value as time passes, and they have large tolerances, typically 20%. Polarity and safety. Due to the construction of electrolytic capacitors and the characteristics of the electrolyte used, electrolytic capacitors must be forward biased. This means that the positive terminal must always be at a higher voltage than the negative terminal if the capacitor becomes reverse biased. Applications of capacitors. There are many applications which do not need tight tolerances and AC polarization, but require large capacitance values. They are commonly used as filtering devices in various power supplies to reduce the voltage ripple. When used in switching power supplies, they are often the critical component limiting the usable life of the power supply, so high quality capacitors are used in this application. They may also be used in input and output smoothing as a low pass filter if the signal is a DC signal with a weak AC component. Power supply circuits, inverters, electric control unit for automotive. There are many types of ECU. Powertrain ECU, motor control ECU, LED lump, airbag. Components tester. A component tester is used to test if components are working correctly in circuit. This is very nice if you do electronic repairs. You can test components directly on a soldered PCB. We can see if components work correctly by comparing them with the same component on a working PCB, or the more difficult way, by analyzing the characteristics. We tell how you can make your component tester if your oscilloscope does not have one. Components for testing CRO. Oscilloscope with 2 channels, 2 XY function, channel invert function, 1K resistor, 12 to 15 volt transformer. Test procedure. Do not test any component in live circuit. Remove all grounds, power and signals connected to the component under test. Set up component tester as stated. Connect test leads across component to be tested. Observe oscilloscope display. Only discharge capacitors should be tested. Test pattern displays. The following test patterns show typical patterns displayed by the various components under test. Open circuit is indicated by a straight horizontal line. Short circuit is shown by a straight vertical line. Testing resistors. The test pattern expected from a resistor is therefore a sloping straight line. The angle of slope is determined by the value of the resistor under test. With high values of resistance, the slope will tend towards the horizontal axis, and with low values, the slope will move towards the vertical axis. Values of resistance from 20 ohm to 4.7 k ohm can be approximately evaluated. The determination of actual values will come with experience or by direct comparison with a component of known value. Testing capacitors and inductors. Capacitors and inductors cause a phase difference between current and voltage, and therefore between the X and Y deflection, giving an ellipse-shaped display. The position and opening width of the ellipse will vary according to the impedance value at 50 Hz of the component under test. A horizontal ellipse indicates high impedance or a relatively small capacitance or a relatively high inductance. A sloping ellipse means that the component has a considerable ohmic resistance in addition to its reactance. The values of capacitance of normal or electrolytic capacitors from 0.1 mu f to 1000 mu f can be displayed and approximate values obtained. Inductive components, coils, transformers can also be tested. Testing semiconductors. Most semiconductor devices such as diodes, Z diodes, transistors, and FETs can be tested. The main characteristic displayed during semiconductor testing is the voltage dependent knee caused by the junction changing from the conducting state to the non-conducting state. It should be noted that both the forward and reverse characteristics are displayed simultaneously. More important is testing components for open or short circuit, which from experience is most frequently needed. Testing diodes. Diodes normally show at least their knee in the forward characteristic. Possibly only a small portion of the knee is visible. Zener diode always shows their forward knee, and depending on the test voltage, the Zener breakdown forms a second knee in the opposite direction. If the breakdown voltage is higher than the positive or negative voltage peak of the test voltage, it cannot be displayed. Testing transistors. 3 different tests can be made to transistors: base emitter, base collector, and emitter collector. The basic equivalent circuit of a transistor is a Z diode between base and emitter, and a normal diode with reverse polarity between base and collector in series connection. These transistor test patterns are valid in most cases, but there are exceptions to the rule. For example, Darlington FETs. In-circuit tests. During in-circuit tests, make sure the circuit is dead. No power from mains or line or battery, and no signal inputs are permitted. Remove all ground connections including safety earth. Pull out power plug from outlet. Remove all measuring cables including probes between oscilloscope and circuit under test. Otherwise, both component tester leads are not isolated against the circuit under test. Open resistors. Current will only flow in a circuit around a continuous path or multiple paths from and back to the source of EMF. Any interruption in the circuit, such as an open switch. Difference between open in series and parallel. The major difference between an open in a parallel circuit and an open in a series circuit is in the parallel circuit, the open would not necessarily disable the circuit. If the open condition occurs in a series portion of the circuit, there will be no current because there is no complete path for current flow. The open occurs in a parallel path, some current will still flow in the circuit. The total resistance of the circuit will increase and total current will decrease. Checking for an open. An open is when two circuit points are not connected when they should be connected. If there is an open, the reading will be infinite, which is displayed by with dashes or something equivalent. If the resistor is in circuit, detecting an open can be difficult. Measuring the resistance. To measure a resistor, place the digital multimeter on the ohms setting that matches the value of the resistor. For example, resistors between 20k ohms and 200k need the meter to be set at the higher level 200k in order to accurately measure resistance. Connect a meter probe to each end of the resistor to get a reading. Voltage drop in open circuit. A battery not connected to anything is a voltage drop on an open circuit. The negative terminal is ground at 0V. The positive terminal is at plus 9V or plus 1.5V or whatever. There is no wire connecting the two terminals, so you have an open circuit. The voltage drop across the positive and negative terminals is 9V. Optocouplers. An opto-isolator, also called an optocoupler, photocoupler or optical isolator, is a component that transfers electric signals between two isolated circuits by using light. Opto-isolators prevent high voltages from affecting the system receiving the signals. A common type of opto-isolator consists of an LED and a phototransistor in the same opaque package. Operations. An opto-isolator contains a source emitter of light, almost always a light emitting diode that converts electrical input signal into light, a closed optical channel and a photosensor which detects incoming light and either generates electric energy directly or modulates electric current flowing from an external power, can transfer the light signal but not transfer the electrical signal. The sensor can be a photoresistor, a photodiode, a phototransistor, a silicon control rectifier SCR or a triac. Electric isolation. The main function of an opto-isolator is to block such high voltages and voltage transients. They contain a single physical isolation barrier but provide protection equivalent to double isolation. An opto-isolator connects input and output sides with a beam of light modulated by input current. It transforms useful input signal into light, sends it across the dielectric channel, captures light on the output side, and transforms it back into electric signal. Types of isolators. The types of isolators are as follows: resistive opto-isolator, diode opto-isolator, transistor opto-isolator, opto-isolated SCR, opto-isolated triac, solid state relay. Types of configuration. The types of configuration are as follows: closed pair configuration, slotted coupler interrupted configuration, reflective pair. The most common sizes for maximum output voltage are 30 volt, 70 volt and 80 volt. The maximum operating temperature can range from 70 C to 150 C, with the most common optocoupler chips having a maximum operating temperature of 100C. Features. The most important feature of an optocoupler is its electricity transfer efficiency. An optocoupler's efficiency is measured through its current transfer ratio, CTR, which is the relationship between the current change on the output side of the barrier and the current change on the input side of the barrier. Most optocouplers work at a CTR between 10 and 50%. Significance of optocouplers. Optocouplers are most often used to separate two circuit elements that are operating on extremely different voltages. This prevents damage to the part working at a lower voltage. They also work to keep the two elements from being damaged by reverse voltage or power surges. Benefits. Optocouplers play integral roles in many common household items such as telephones, cellular phones, computer circuits, internet modems, and even the entire house electrical circuit. Optocouplers have also become essential to modern televisions as the technology and complexity of digital components has grown. Uses of optoisolator. The applications of optoisolator are as follows: phototransistor optocoupler, input-output switching circuit, microcontrollers, DC and AC power control, signal isolation, power supply regulation. Piezoelectric transducers. The sound source of a piezoelectric sound component is a piezoelectric diaphragm. A piezoelectric diaphragm consists of a piezoelectric ceramic plate which has electrodes on both sides and a metal plate. Applying DC voltage between electrodes of a piezoelectric diaphragm causes mechanical distortion due to the piezoelectric effect. Soldering procedures. A lead wire is needed to apply voltage to the piezoelectric diaphragm. While using a soldering iron, the optimum temperature for soldering a lead wire to a metal plate is 320 to 350 degrees centigrade for 3 seconds, and the same temperature for the ceramic electrode for 0.5 seconds or less. The lead wire should be as fine as possible as it works as a load restricting oscillation of the piezoelectric diaphragm. Design procedures. The resonant frequency depends on methods used to support the piezoelectric diaphragm. If piezoelectric diaphragms are of the same shape, their values will become smaller. Since the piezoelectric diaphragm and cavity have proper resonant frequencies, sound pressure in specific frequencies can be increased, and a specific bandwidth can be provided by controlling both positions. Drive procedures. The types of drive procedures are as follows. External drive method. This method produces sound by driving the piezoelectric diaphragm with electric signals supplied from an external oscillating circuit, such as a multi-vibrator. Self-drive method. When the frequency is closed to the resonant frequency, the circuit satisfies oscillating conditions and the piezoelectric diaphragm is driven with the oscillating frequency. Mechanism of producing sound. When a voltage is applied across the piezoelectric ceramics, it stretches in its plane. When a voltage is applied to the piezoelectric diaphragm, as the metal plate does not stretch, it bends. When the polarity of the applied voltage is reversed, the piezoelectric ceramic shrinks and the metal plate bends towards the opposite. When the direction of applied voltage changes alternately, producing sound waves in the air. Properties of piezoelectric diaphragms. Diameter, density, thickness, Poisson ratio, elastic modulus. Piezo buzzers. A piezoelectric element may be driven by an oscillating electronic circuit or other audio signal source driven with a piezoelectric audio amplifier. Sounds commonly used to indicate that a button has been pressed are a click, a ring, or a beep. The piezo buzzer produces sound based on reverse of the piezoelectric effect. The generation of pressure variation or strain by the application of electric potential across a piezoelectric material is the underlying principle. Piezo buzzers. These buzzers can be used to alert a user of an event corresponding to a switching action, counter signal or sensor input. They are also used in alarm circuits. The buzzer produces the same noisy sound irrespective of the voltage variation applied to it. It consists of piezo crystals between two conductors. When a potential is applied across these crystals, they push on one conductor. This push and pull action results in a sound wave. Most buzzers produce sound in the range of 2 to 4 kHz. Features: the PS series are high-performance buzzers that employ piezoelectric elements and are designed for easy incorporation into various circuits. They feature extremely low power consumption in comparison to electromagnetic units. Because these buzzers are designed for external excitation, the same part can serve as both a musical tone oscillator and a buzzer. They can be used with automated inserters. Moisture-resistant models are also available. The lead wire type PS1550L40N with both-sided adhesive tape installed easily is prepared. Working: piezo buzzer is an electronic device commonly used to produce sound. Lightweight, simple construction and low price makes it usable in various applications like car or truck reversing indicator, computers, call bells, etc. Piezo buzzer is based on the inverse principle of piezoelectricity. It is the phenomena of generating electricity when mechanical pressure is applied to certain materials, and the vice versa is also true. Working: such materials are called piezoelectric materials. Piezoelectric materials are either naturally available or man-made. Piezoceramic is class of man-made material which possesses piezoelectric effect and is widely used to make disc, the heart of piezo buzzer. When subjected to an alternating electric field, they stretch or compress in accordance with the frequency of the signal, thereby producing sound. Piezo buzzer as sensor. Piezo buzzers exhibit the reverse piezoelectric effect. The normal piezoelectric effect is generating electricity from squeezing a crystal. Can get several thousand volts. Makes a spark. Applications. The applications are as follows. They are used for quality assurance process control and for research and development in many industries. In medical, instrumentation and aerospace industries. In the automotive industry, piezo buzzers are used to monitor combustion when developing combustion engines. The rise of piezoelectric technology is directly related to a set of inherent advantages. The high modulus of elasticity of many piezoelectric materials is comparable to that of many metals and goes up to 10 to the power of 6 N per meter square. It is insensitive to electromagnetic radiations and fields, enabling measurements under harsh conditions. Disadvantages. One disadvantage of piezoelectric sensor is that they cannot be used for truly static measurements. A static force will result in a fixed amount of charges on the piezoelectric material. While working with conventional readout electronics, imperfect insulating materials and reduction in internal sensor resistance will result in a constant loss of electrons and yielding a decreasing signal. Potentiometers. A potentiometer, informally a pot, is a 3-terminal resistor with a sliding contact that forms an adjustable voltage divider. A potentiometer, measuring instrument, is essentially a voltage divider used for measuring electric potential. Potentiometers are commonly used to control electric devices such as volume controls on audio equipment. Potentiometers operate by a mechanism which can be used as position transducers. Constructions. Many inexpensive potentiometers are constructed with a resistive element formed into an arc of a circle, usually a little less than a full turn, and a wiper sliding on this element when rotated, making electrical contact. The resistive element with a terminal at each end is flat or angled. The wiper is connected to a third terminal usually between the other two. On panel potentiometers, the wiper is usually the central terminal of 3. For single turn potentiometers, this wiper typically travels just under 1 revolution around the contact. The only point of ingress for contamination is the narrow space between the shaft and the housing it rotates in. Multi-turn potentiometers, both user-accessible and preset, allow finer adjustments. Rotation through the same angle changes the setting by typically a tenth as much as for a simple rotary potentiometer. Theory of operation. The potentiometer can be used as a voltage divider to obtain a manually adjustable output voltage at the slider wiper from a fixed input voltage applied across the two ends of the potentiometer. Types of potentiometer. There are 3 types of potentiometer: wire wound potentiometer, carbon film potentiometer, plastic film pots, rotary, linear. Applications. The applications are as follows: audio control, television, motion control, transducers, computation. Characteristics. The characteristics of potentiometer are as follows: taper, marking codes, resolution, hop on and hop off resistance. Potentiometer. Potentiometers are used as follows: transducers. To measure the displacement of the body, this body which is moving is connected to the sliding element of the potentiometer. Sensors. A sensor is a device that detects and responds to some type of input from the physical environment. Soldering. Soldering is a process in which 2 or more metal items are joined together by melting and flowing a filler metal solder into the joint, the filler metal having a lower melting point than the adjoining metal. Soldering differs from welding in that soldering does not involve melting the work pieces. In brazing, the filler metal melts at a higher temperature, but the workpiece metal does not melt. Soldering concepts. Solder is used to hold 2 or more conductors in electrical contact with each other. Solder is not used to make the electrical contact. Solder is not used to provide the main mechanical support for a joint. Solder is used to encapsulate a joint, prevent oxidation of the joint, and provide minor mechanical support for a connection. Soldering process. Turn on soldering iron and let it get to temperature. Clean soldering tip with a damp cloth or sponge. Install the component and hold in place with a physical connection. Heat the component lead and the adjacent circuit board pad. Apply the right amount of heat. Touch solder to the component lead and pad. Melt the right amount of solder. Remove solder. Remove heat. Hold steady until cool. Inspect the connection. Art and good eye. Process in soldering. Insert component from the component side of the PCB and bend leads out to physically hold the component steady and in place. When you can't bend leads, tack solder one lead to hold component in place. Touch the tip to the component lead and the pad. Apply just enough heat. When you have headed the joint just the right amount, touch solder to lead and pad. The melting solder will flow around the joint, called wetting. Remove solder, then tip and allow joint to cool. Process. There are 3 forms of soldering: soft soldering, which uses a tin lead alloy; silver soldering, which uses silver; brazing, which uses a brass alloy. Silver soldering. Hard soldering or silver soldering is used to join precious and semi-precious metals such as gold, silver, brass, and copper. The solder is usually referred to as easy, medium, or hard. This refers to its melting temperature and not the strength of the joint. Extra easy solder contains 56% silver and has a melting point of 1145 degree Fahrenheit or 618 degree centigrade. Extra hard solder has 80% silver and melts at 1370 degree Fahrenheit or 740 degree centigrade. If multiple joints are needed, then the jeweler will start with hard or extra hard solder and switch to lower temperature solders for later joints. Silver solder is absorbed by the surrounding metal, resulting in a joint that is actually stronger than the metal being joined. The metal being joined must be perfectly flush, as silver solder cannot normally be used as filler. Advantages of soldering: lower heat. Soldering requires temperatures around 400 degree Fahrenheit. Welding requires far higher heat. Does not warp. Since solder flows at lower temperatures, the metals connected do not melt or warp. They maintain their original size and shape even if the person soldering makes mistakes. Solder conducts electricity. The solder flows between electrical connectors to bond them together. Since the solder is metal, it conducts electricity. Multiple connections. Circuit boards floated on a molten solder bath make multiple connections with a single operation. The solder only sticks to the components and not the board itself. Easy to learn. Soldering does not require any particular skill. You can learn to solder electronic components, plumbing, and jewelry with easy to follow instructions found on several websites. Disadvantages: difficult to disconnect. Soldered connections cannot be easily disconnected, and removing the solder sometimes causes irreparable physical and electrical damage. Burns insulation. Tiny wires such as those found in telephone switching offices have thin insulation that can melt or burn off easily. Wire wrapping has replaced soldering wires in many industrial applications. Damage to adjacent components. Requires power. Many types of electrical connections can be made with nuts and bolts. There is no need to have electrical power to run a soldering iron when using nuts and bolts. Difficult to repair. Printed circuit boards can only stand so much heat before the circuit traces either lift off or burn. Lead. Many types of solder contain lead, which is a poison. Applications. Soldering is used in plumbing, electronics, and metalwork, from flashing to jewelry. Soldering provides reasonably permanent but reversible connections between copper pipes in plumbing systems, as well as joints in sheet metal objects such as food cans, roof flashing rain gutters, and automobile radiators. Jewelry components. Spark gaps. A spark gap consists of an arrangement of two conducting electrodes separated by a gap, usually filled with a gas such as air, designed to allow an electric spark to pass between the conductors. When the voltage difference between the conductors exceeds the gap's breakdown voltage, a spark forms, ionizing the gas and drastically reducing its electrical resistance. Potentiometers. An electric current then flows until the path of ionized gas is broken or the current reduces below a minimum value called the holding current. Spark gaps were used in early electrical equipment such as spark gap radio transmitters, electrostatic machines, and X-ray machines. Their most widespread use today is in spark plugs to ignite the fuel in internal combustion engines, but they are also used in lightning arresters and other devices to protect electrical equipment from high voltage transients. Spark visibility. The light emitted by a spark does not come from the current of electrons itself, but from the material medium fluorescing in response to collisions from the electrons. When electrons collide with molecules of air in the gap, they excite their orbital electrons to higher energy levels. When these excited electrons fall back to their original energy levels, they emit energy as light. It is impossible for a visible spark to form in a vacuum. Applications. The applications are as follows: ignition devices, protective devices, high-speed photography, radio transmitters, spear gap for voltage measurement, power switching devices, visual entertainment. Health hazards. Exposure to an arc-producing device can pose health hazards. In a closed space such as a classroom or home, the continuous arc formation of an open-air Jacob's ladder will ionize oxygen and nitrogen, which then reforms into reactive molecules such as ozone and nitric oxide. These free radicals can be damaging to the mucous membranes of people near the spark gap. Plants are also susceptible to ozone poisoning. These hazards are not present when the arc is formed outdoors, since the heated ionized gases will rise up into the air and dissipate into the atmosphere. Spark gaps, which only intermittently produce short spark bursts, are also minimally hazardous because the volume of ions generated is very small. Super probe. To assist in testing the circuit, you will need a 3-volt supply with a 220 R series resistor. This is called a tester. Remove the chip and place the positive of the tester on one pin of the IC socket and negative on a pin of the display to illuminate segment A. Go through the pins to check all the other segments. Without the chip, turn the project on to make sure the regulator is providing 5 volt. The program. The program is complex because it is carrying out operations of a very complex nature. The only way you can study the program is to select a particular function and remove all the other subroutines. Burn a new chip to make sure the function works, then print out the program so it can be studied. Modify the program. The kit comes with a pre-programmed PIC chip, but if you want to program your own chip or modify the program, the .hex file is available as well as the assembly file, so you can see how the program has been written and view the comments. The program consists of a large number of subroutines, and this requires looking up and down the program. There is only 30 empty locations in program memory, so you have very little space to add any new feature. However, the one thing you can do is change some of the values in a subroutine and see what effect it has on the program. This is the only way to start a modification. To burn program a blank PIC 16F870, you will need a programmer. Surface mount packs. Surface mount technology, SMT, is a method for producing electronic circuits in which the components are mounted or placed directly onto the surface of printed circuit boards or PCBs. An electronic device so made is called a surface mount device, SMD. In the industry, it has largely replaced the through-hole technology construction method of fitting components with wire leads into holes in the circuit board. Both technologies can be used on the same board for components not suited to surface mounting, such as large transformers and heat-sinked power semiconductors. An SMT component is usually smaller than its through-hole counterpart because it has either smaller leads or no leads at all. It may have short pins or leads of various styles, flat contacts, and a matrix of solder balls, BGAs, or terminations on the body of the component. It is called as planar mounting. Assembly techniques. Where components are to be placed, the printed circuit board normally has flat, usually tin lead, silver, or gold-plated copper pads without holes, called solder pads. Solder paste, a sticky mixture of flux and tiny solder particles. It can also be applied by a jet printing mechanism similar to an inkjet printer. The components to be placed on the boards are usually delivered to the production line in either paper or plastic tapes, wound on reels or plastic tubes. Rework. There are essentially two non-contact soldering or desoldering methods: infrared soldering, soldering with hot gas. Infrared. With infrared soldering, the energy for heating up the solder joint is transmitted by long or short wave infrared electromagnetic radiation. Hot gas. During hot gas soldering, the energy for heating up the solder joint is transmitted by a hot gas. This can be air or inert gas. Packages. There are many types of packages. They are 2-terminal packages, 3-terminal packages, 5 and 6-terminal packages, more than 6-terminal packages. Identification. Resistors. For 5% precision, SMD resistors usually are marked with their resistance values using 3 digits, 2 significant digits, and a multiplier digit. The block or colored coating on one face of the device. The sides and other face simply being the uncoated, usually white ceramic substrate. The coated surface with the resistive element beneath is normally positioned face up when the device is soldered to the board. Capacitor. Non-electrolytic capacitors are usually unmarked, and the only reliable method of determining their value is removal from the circuit and subsequent measurement with a capacitance meter or impedance bridge. The materials used to fabricate the capacitors, such as nickel tantalate, possess different colors, and these can give an approximate idea of the component. Some film or tantalum electrolytic types are unmarked and possess orange or blue body colors. Inductor. SMT inductor, larger inductance values often have turns of wire or flat strap around the body or embedded in clear epoxy, allowing the wire or strap to be seen. These higher inductance types are often limited to small current range. Some of the flat strap types can handle a few amps. Discrete semiconductors. Discrete semiconductors such as transistors, diodes, and FETs are often marked with a 2 or 3 symbol code in which the same code marked on different packages or on devices made by different manufacturers can translate to different devices. Many of these codes used because the devices are too small to be marked with more traditional numbers used on through-hole equivalent devices. Advantages. Lower initial cost and time of setting up for production. Fewer holes need to be drilled. Simpler and faster automated assembly. Some placement machines are capable of placing more than 136,000 components per hour. Small errors in component placement are corrected automatically as the surface tension of molten solder pulls components into alignment with solder pads. Components can be placed on both sides of the circuit board. Lower resistance and inductance at the connection, consequently, fewer unwanted RF signal effects, and better and more predictable high-frequency performance. Better mechanical performance under shake and vibration conditions. Disadvantages. Manual prototype assembly or component level repair is more difficult and requires skilled operators and more expensive tools due to the small sizes and lead spacings of many SMDs. SMD solder connections may be damaged by potting components going through thermal cycling. SMT is unsuitable for large, high power or high voltage parts, for example, in power circuitry. Transformers. A transformer is an electrical device that transfers energy between two circuits through electromagnetic induction. A transformer most commonly consists of two windings of wire that are wound around a common core to provide tight electromagnetic coupling between the windings. The core material is often a laminated iron core. Transformers. The coil that receives the electrical input energy is referred to as the primary winding, while the output coil is called the secondary winding. A transformer cannot operate with direct current, although when it is connected to a DC source, a transformer typically produces a short output pulse as the current rises. The varying electromagnetic field in the vicinity of the secondary winding induces an electromotive force in the secondary winding, which appears a voltage across the output terminals. Principles. The functioning of a transformer is based on two principles of the laws of electromagnetic induction. An electric current through a conductor, such as a wire, produces a magnetic field surrounding the wire, and a changing magnetic field in the vicinity of a wire induces a voltage across the ends of that wire. Principles. The magnetic field excited in the primary coil gives rise to self-induction as well as mutual induction between coils. This self-induction counters the excited field to such a degree that the resulting current through the primary winding is very small when no load draws power from the secondary winding. Ideal transformers. The characteristics of the ideal transformers are: the windings of the transformer have no resistance, thus there is no copper loss in the winding and hence no voltage drop. Flux is confined within the magnetic core, therefore it is the same flux that links the input and output windings. Permeability of the core is infinitely high. The transformer core does not suffer magnetic hysteresis or eddy currents which cause inductive loss. Main constructional parts of transformers. Primary winding of transformer, which produces magnetic flux when it is connected to electrical source. Magnetic core of transformer. The magnetic flux produced by the primary winding will pass through this low reluctance path linked with secondary winding and creates a closed magnetic circuit. Secondary winding of transformer. Working. The working principle of transformer is very simple. It depends upon Faraday's law of electromagnetic induction. Actually, mutual induction between two or more windings is responsible for transformation action in an electrical transformer. Losses in transformer. The following are losses in transformers: hysteresis losses, copper loss, eddy current loss, iron loss, core loss. Types of transformers. The types of transformers are as follows: auto transformer, capacitor voltage transformer, power transformer, polyphase transformer, leakage transformer, audio transformer, resonant transformer, output transformer. Applications. Transformers perform voltage conversion, isolation protection, and impedance matching. In terms of voltage conversion, transformers can step up voltage or step down current from generators to high voltage transmission lines, and step down voltage or step up current to local distribution circuits or industrial customers. The step up transformer is used to increase the secondary voltage related to the primary voltage, whereas the step down transformer is used to decrease the secondary voltage relative to the primary voltage. Applications. Transformers range in size from thumbnail sized used in microphones to units weighing hundreds of tons interconnecting the power grid. A broad range of transformer designs are used in electronic and electrical power applications, including miniature, audio, isolation, high frequency, power conversion transformers, etc. Transformers are also used extensively in electronic products to step down. Applications. The transformer also electrically isolates the end user from contact with the supply voltage. Signal and audio transformers are used to couple stages of amplifiers and to match devices such as microphones and record players to the input of amplifiers. Voltage regulators. A voltage regulator is designed to automatically maintain a constant voltage level. A voltage regulator may be simple feed-forward design or may include negative feedback control loops. It may use an electromechanical mechanism or electronic components. Depending on the design, it may be used to regulate one or more AC or DC voltages. Parameters. The important parameters are: load regulation is the change in output voltage for a given change in load current. Line regulation or input regulation is the degree to which output voltage changes with input, that is supply voltage changes, as a ratio of output to input change. Supply coefficient of the output voltage is the change with temperature, perhaps averaged over a given temperature range. Initial accuracy of a voltage regulator reflects the error in output voltage for a fixed regulator without taking into account temperature or aging effects on output accuracy. Absolute maximum ratings are defined for regulator components, specifying the continuous and peak output currents that may be used, the maximum input voltage, maximum power dissipation at a given temperature, etc. Output noise and output dynamic impedance may be specified as graphs versus frequency, while output ripple noise may be given as peak to peak or RMS voltages. Electronic voltage regulators. A simple voltage regulator can be made from a resistor in series with a diode or series of diodes. Due to the logarithmic shape of diode VI curves, the voltage across the diode changes only slightly due to changes in current drawn or changes in the input. When precise voltage control and efficiency are not important, this design may work fine. Feedback voltage regulators operate by comparing the actual output voltage to some fixed reference voltage. Any difference is amplified and used to control the regulation element in such a way so as to reduce the voltage error. Active regulators. Active regulators employ at least one active amplifying component, such as a transistor or operational amplifier. Shunt regulators are often, but not always, passive and simple, but always inefficient because they essentially dump the excess current not needed by the load. Linear series regulators, switching regulators, SCR regulators. DC voltage. Many simple DC power supplies regulate the voltage using a shunt regulator, such as a Zener diode, avalanche breakdown diode, or voltage regulator tube. Each of these devices begins conducting at a specific voltage and will conduct as much current as required to hold its terminal voltage to that specified voltage. The power supply is designed to only supply a maximum amount of current that is within the safe operating capability of the shunt regulating device, commonly by using a series resistor. Linear regulators. Linear regulators are based on devices that operate in their linear region. In the past, one or more vacuum tubes were commonly used as the variable resistance. Modern designs use one or more transistors instead, perhaps with an integrated circuit. Linear designs have the advantage of output with little noise introduced into their DC output, but are most often much less efficient and unable to step up or invert the input voltage like switched supplies. All linear regulators require a higher input than the output. Switching regulators. Switching regulators rapidly switch a series device on and off. The duty cycle of the switch sets how much charge is transferred to the load. This is controlled by a similar feedback mechanism as in a linear regulator. Because the series element is either fully conducting or switched off, it dissipates almost no power. This is what gives the switching design its efficiency. Switching regulators are also able to generate output voltages which are higher than the input or of opposite polarity, something not possible with a linear design. SCR regulators. Regulators powered from AC power circuits can use silicon-controlled rectifiers as the series device. Whenever the output voltage is below the desired value, the SCR is triggered, allowing electricity to flow into the load until the AC mains voltage passes through zero. SCR regulators have the advantages of being both very efficient and very simple, but because they cannot terminate an ongoing half cycle of conduction, they are not capable of very accurate voltage regulation in response to rapidly changing loads. Applications. The following applications are industrial, automation, lighting, data processing, medical, motor control and drives, power management, smart grid, renewable energy. Voltage. Voltage, electrical potential difference, electric tension or electric pressure, denoted as delta V and measured in units of electrical potential. Volts or joules per coulomb is the electric potential difference between 2 points, or the difference in electric potential energy of a unit charge transported between 2 points. Voltage is equal to the work done per unit charge against a static electric field to move the charge between 2 points. Voltage on a series circuit. Series circuits are sometimes called current coupled or daisy chain coupled. The current in a series circuit goes through every component in the circuit. Therefore, all of the components in a series connection carry the same current. There is only one path in a series circuit in which the current can flow. Voltage in a parallel circuit. If two or more components are connected in parallel, they have the same potential difference across their ends. The potential differences across the components are the same in magnitude and they also have identical polarities. Voltage. In a parallel circuit, the voltage is the same for all elements. V is equal to V1 is equal to V2 is equal to Vn. Measuring instruments. For measuring voltages include the voltmeter, the potentiometer and the oscilloscope. The voltmeter works by measuring the current through a fixed resistor, which according to Ohm's law is proportional to the voltage across the resistor. The potentiometer works by balancing the unknown voltage against a known voltage in a bridge circuit. The cathode ray oscilloscope works by amplifying the voltage and using it to deflect an electron beam from a straight path so that the reflection of the beam is proportional to the voltage. Applications. A common use of the term voltage is in describing the voltage dropped across an electrical device such as a resistor. The voltage drop across the device can be understood as a difference between measurements at each terminal of the device with respect to a common reference point or ground. The voltage drop is the difference between the true readings. Yoke. It is one part of DC motor. DC motor works on the principle that like magnet poles repel and unlike magnetic poles attract each other. A coil of wire with a current running through it generates an electromagnetic field aligned with the center of the coil. By switching the current on or off in a coil, its magnet field can be switched on or off, or by switching the direction of the current in the coil, the direction of the generated magnetic field can be switched 180 degrees. yoke of DC motor. The magnetic frame or yoke of DC motor is made up of cast iron or steel and forms an integral part of the stator or the static part of the motor. Its main function is to form a protective covering over the inner sophisticated parts of the motor and provide support to the armature. It also supports the field system by housing the magnetic poles and field winding of the DC motor. Types of yoke in DC motor. There are two types of yokes in DC motor: laminated yoke DC motor, solid yoke DC motor. Specifications of laminated yoke: range, frame size 80 to 100, voltage 180 volts, output 0.37 to 30 kilowatts, cooling IC 01/06, mounting B3, B5, B35V. Applications of laminated yoke: plastic extrusion, machineries, printing and paper machineries, wire drawing machineries. Features of solid yoke design: low cost design, suitable for application where size is not a criteria, suitable for DC supply with less ripple. Range: kW 1.5 to 600, frame 122 to 160, duty S1 or S4 or S5, armature voltage 110 to 1100, excitation voltage 180 to 360, mounting B3, B5, B35. Applications: steel mill drives, cement mill drives, test rigs, mining. Audio stages. An audio power amplifier is an electronic amplifier that amplifies low power audio signals. Signals composed primarily of frequencies between 20 to 20,000 Hz, the human range of hearing, to a level suitable for driving loudspeakers. It is the final electronic stage in a typical audio playback chain. The preceding stages in such a chain are low power audio amplifiers which perform tasks like preamplification. History. The audio amplifier was invented in 1909 by Lee de Forest when he invented the triode vacuum tube. The triode was a three-terminal device with a control grid that can modulate the flow of electrons from the filament to the plate. The triode vacuum amplifier was used to make the first AM radio. Early audio power amplifiers were based on vacuum tubes, and some of these achieved notably high quality. Most modern audio amplifiers are based on solid-state devices, transistors such as BJTs, FETs, and MOSFETs. But there are still some who prefer tube-based amplifiers and the valve sound. Audio power amplifiers based on transistors became practical with the wide availability of inexpensive transistors in the late 1960s. Filters and preamplifiers. Since modern digital devices, including CD and DVD players, radio receivers, and tape decks, already provide a flat signal at line level, the preamp is not needed other than as a volume control and source selector. One alternative to a separate preamp is to simply use passive volume and switching controls, sometimes integrated into a power amplifier to form an integrated amplifier. Applications. Some important applications include public address systems, theatrical and concert sound reinforcement systems, and domestic systems such as a stereo or home theater system. Instrument amplifiers including guitar amplifiers and electric keyboard amplifiers also use audio power amplifiers. In some cases, the power amplifier for an instrument is integrated into a single amplifier head which contains a preamplifier, tone controls, and electronic effects. Design. Key design parameters for audio power amplifiers are frequency response, gain, noise, and distortion. These are interdependent. Increasing gain often leads to undesirable increases in noise and distortion. While negative feedback actually reduces the gain, it also reduces distortion. Most audio amplifiers are linear amplifiers operating in class AB. Audio power amplifier classes. The audio power amplifier classes are as follows: Class A, Class B, Class AB, Class G, Class H, Class D. Power amplifier classes A. Class A. Key ingredient of Class A operation is that output device is always on. Single-ended design with only one type polarity output device. The most inefficient of all power amplifier designs, averaging only around 20%, are inherently the most linear with the least amount of distortion. Impractical for professional audio applications due to inefficiency. power amplifier classes B. Class B, opposite of class A, both output devices are never allowed to be on at the same time. Each output device is on for exactly one half of a complete sinusoidal signal cycle. Class B designs show high efficiency but poor linearity across the crossover region. Class B designs restricted to low power applications, for example, battery operated equipment such as communications audio. Power amplifier classes AB. Class AB, intermediate case, both devices are allowed to be on at the same time but just barely. Output bias is set so that current flows in a specific output device appreciably more than a half cycle but less than the entire cycle. The inherent non-linearity of Class B designs is eliminated without the gross inefficiencies of the Class A design. Power amplifier classes G. Operation involves changing the power supply voltage from a lower level to a higher level when larger output swings are required. Common for pro audio designs. Power amplifier classes H. Take the Class G design one step further and actually modulates the higher power supply voltage by the input signal. Allows the power supply to track the audio input and provide just enough voltage for optimum operation of the output devices. Power amplifier classes D. Operation is switching, hence the term switching power amplifier. Output devices are rapidly switched on and off at least twice for each cycle. The output devices are either completely on or completely off, so theoretically they do not dissipate any power. Class D complications. Need to operate at high switching speed, for example 250 kHz for full audio bandwidth, 20 kHz reproduction with low distortion. Traditional design requires dead time between positive and negative polarity phases. Class S, first invented in 1932, used for both amplification and amplitude modulation. Similar to Class D, except the rectangular PWM voltage waveform is applied to low pass filter that allows only the slowly varying DC or average voltage component to appear across the load. Class I, when used with fixed frequency naturally sampled two-sided PWM, it forms a theoretically optimum converter. It is also called as a balanced current amplifier. Burnt resistor. We can find burnt resistor by three methods as follows. Method 1. Scarp the outer coating. Clean the burnt section of the resistor. Measure resistance from one end of the resistor to the damaged section. Again, measure the resistance from damaged section to the other end of the resistor. Add these two values of resistances. This is the approximate value of burnt resistor. Just add a small value of resistance for damaged section. That is, suppose the value of burnt resistor was 1 kilo ohms, but you got 970 ohms. So add 30 ohms and you will have 1 kilo ohms. Method 2. This method can also be used for finding the value of resistors, also for connected resistors in the circuit if you don't know about resistance color coding. Connect resistor to multimeter and measure voltage drop across resistor. Now measure the current flowing into the resistor. Multiply both values and you will get the wattage of resistor as P is equal to VI. This wattage must be less than the wattage of the resistor being replaced. Method 3. This method can be better used if you know the expected output voltage of the circuit and you have resistors set of same wattage as burnt resistor. Perform this method if you don't know the value of resistor. Start with a high value of resistance and temporarily connect this resistor instead of burnt resistor. Measure the expected output voltage of the circuit. If you obtain same voltage as expected voltage, then you have done. If you don't know about the expected voltage, then keep reducing the value of resistor until you satisfy with work of circuit for which purpose it was designed. Applications. The applications are as follows. Heaters, fuse, sensors, light. Battery. An electric battery is a device consisting of one or more electrochemical cells that convert stored chemical energy into electrical energy. Each cell contains a positive terminal or cathode and a negative terminal or anode. Electrolytes allow ions to move between the electrodes and terminals, which allows current to flow out of the battery to perform work. Principle of operation. Batteries convert chemical energy directly to electrical energy. A battery consists of some number of voltaic cells. Each cell consists of two half cells connected in series by a conductive electrolyte containing anions and cations. One half cell includes electrolyte and negative electrode, the electrode to which anions, negatively charged ions, migrate. The other half cell includes electrolyte and the positive electrode to which cations migrate. The electrodes do not touch each other but are electrically connected by the electrolyte. Some cells use different electrolytes for each half cell. A separator allows ions to flow between half cells but prevents mixing of the electrolytes. Each half cell has an electromotive force. Types of batteries. Batteries are classified into primary and secondary forms. Primary batteries, it is irreversibly transform chemical energy to electrical energy. When the supply of reactants is exhausted, energy cannot be readily restored to the battery. Secondary batteries, it can be recharged, that is, they can have their chemical reactions reversed by supplying electrical energy to the cell, approximately restoring their original composition. Primary batteries. Primary batteries or primary cells can produce current immediately on assembly. These are most commonly used in portable devices that have low current drain, are used only intermittently, or are used well away from an alternative power source, such as in alarm and communication circuits where other electric power is only intermittently available. Disposable primary cells cannot be reliably recharged since the chemical reactions are not easily reversible and active materials may not return to their original forms. Battery manufacturers recommend against attempting recharging primary cells. Secondary batteries. Secondary batteries, also known as secondary cells or rechargeable batteries, must be charged before first use. They are usually assembled with active materials in the discharged state. Rechargeable batteries are charged by applying electric current which reverses the chemical reactions that occur during discharge or use. Devices to supply the appropriate current are called chargers. The oldest form of rechargeable battery is the lead-acid battery. Battery cell types. Types of battery cells are wet cell, dry cell, molten salt, reserve. Self-discharge. Disposable batteries typically lose 8 to 20% of their original charge per year at room temperature, that is 20 to 30 degrees centigrade, due to non-current producing side chemical reactions that occur within the cell even when no load is applied. The rate of side reactions is reduced for batteries if they are stored at lower temperatures, although some can be damaged by freezing. Sizes. Primary batteries readily available to consumers range from tiny button cells used for electric watches to the number 6 cell used for signal circuits or other long duration applications. Secondary cells are made in very large sizes. Very large batteries can power a submarine or stabilize an electrical grid and help level out peak loads. Test conditions. In all of the following tests and testing in general, the test conditions must be specified so that repeatable results can be obtained and meaningful comparisons can be made. This includes factors such as method, temperature, and DOD, load and duty cycle. For instance, the cell capacity and cycle life, two key performance indicators, could vary by 50% or more depending on the temperature and the discharge rate at which the tests were carried out. Battery specification should always include the test conditions to avoid ambiguity. Qualification testing. Qualification testing is designed to determine whether a cell or battery is fit for the purpose for which it was intended before it is approved for use in the product. This is particularly important if the cell is to be used in a mission-critical application. These are comprehensive tests carried out initially on a small number of cells, including testing some of them to destruction if necessary. As a secondary stage, qualification also includes testing finished battery packs before the product is approved for release to the customer. The tests are usually carried out to verify that the cells meet the manufacturer's specification, but they could also be used to test the cells to arbitrary limits set by the applications engineer to determine how long the cells survive under adverse conditions or unusual loads, to determine failure modes or safety factors. The battery packs should also be tested with a charger recommended for the application to ensure compatibility. Shake and bake. Mechanical testing. Typical tests are included in the safety standards below. They include simple tests for dimensional accuracy to dynamic testing to verify that the product can survive any static and dynamic mechanical stresses to which it is subject. Environmental testing. Typical tests are included in the safety standards below. They are designed to exercise the product through all the environmental conditions likely to be encountered by the product during its lifetime. Cycle testing. Cycle testing is usually carried out on banks of cells using multi-channel testers which can create different charge and discharge profiles, including pulsed inputs and loads. At the same time, various cell performance parameters such as temperature, capacity, impedance, and power output and discharge time can be monitored and recorded. Typically, it takes about 5 hours for a controlled full charge discharge cycle. This means testing to 1000 cycles will take 208 days, assuming working 7 days per week, 24 hours per day. Thus, it takes a long time to verify the effect of any ongoing improvements made to the cells. Load testing. Load testing is used to verify that the battery can deliver its specified power when needed. The load is usually designed to be representative of the expected conditions in which the battery may be used. It may be a constant load at the C rate or pulsed loads at higher current rates, or in the case of automotive batteries, the load may be designed to simulate a typical driving pattern. Low power testing is usually carried out with resistive loads. For very high power testing with variable loads, other techniques may be required. Inspection and production testing. The purpose of inspection production testing is to verify that the cells which have been purchased and the products built with them conform to agreed specifications. These tend to be short tests carried out on 100% of the throughput or on representative samples. The composition of the materials from which the components are made should not be overlooked. We have seen examples of unscrupulous suppliers plating connectors with a gold-colored alloy rather than the gold specified, and using cheap plastics which buckle in the heat rather than the high-quality plastics required. Typical tests include both mechanical and electrical tests. The components are checked for dimensional accuracy, and sample subassemblies are subject to weld strength testing of the interconnections. Electrical parameters measured include the internal impedance and the output voltage of the cell or battery pack with or without a load. The battery is also submitted to short duration charging and discharging pulses of about 2 milliseconds to check that the unit accepts and can deliver charge. Performance monitoring. Performance monitoring is used to verify whether the cell is continuing to perform as required once it is in use in the application for which it was specified. These are individual tests specified by the user. There are no simple direct measurements, such as placing a voltmeter across the terminals to determine the condition of the battery. The voltmeter reading may tell us something about the state of charge with an enormous margin of error, but it cannot tell us how well the battery will deliver current when demanded. Internal resistance. To determine the internal resistance, first it is necessary to measure the open circuit voltage of the cell. Then, a load should be connected across the cell, causing a current to flow. This will reduce the cell voltage due to the IR voltage drop across the cell, which corresponds to the cell's internal resistance. The cell voltage should then be measured again when the current is flowing. The resistance is calculated by Ohm's law from the voltage difference between the two measurements and the current which is flowing through the cell. Open circuit voltage, OCV. Measuring a battery's open circuit voltage is not a reliable measure of its ability to deliver current. As a battery ages, its internal resistance builds up. This will reduce the battery's ability to accept and to hold charge, but the open circuit voltage will still appear normal despite the reduced capacity of the battery. Comparing the actual internal resistance with the resistance of a new battery will provide an indication of any deterioration in battery performance. Impedance and conductance testing. Battery manufacturers have their own definitions and conventions for impedance and conductance based on the test method used. Though not strictly correct, they serve their purpose. The test method involves applying a small AC voltage E of known frequency and amplitude across the cell and measuring the in-phase AC current I that flows in response to it. The impedance Z is calculated by Ohm's law to be Z is equal to E by I. The conductance C is similarly calculated as C is equal to I by E. DC measurements. Using a conventional ohm meter for measuring the resistance of the cables, contacts and intercell links is not satisfactory because the resistance is very low and the resistance of the instrument leads and the contacts causes significant errors. More accuracy can be achieved by using a Kelvin bridge which separates the voltage measuring leads from the current source leads and thus avoids the error caused by the volt drop along the current source leads. Failure analysis. Cell failure analysis is best carried out by the cell manufacturers. Only they will have the detailed specifications of the cell mechanical and chemical components, and it normally requires access to expensive analytical equipment such as electron microscopes and mass spectrometers, which they should be expected to have. Cells. A primary cell or battery is one that cannot easily be recharged after one use and are discarded following discharge. Most primary cells utilize electrolytes that are contained within absorbent material or a separator, that is, no free or liquid electrolyte, and are thus termed dry cells. Secondary cells. A secondary cell or battery is one that can be electrically recharged after use to their original pre-discharge condition by passing current through the circuit in the opposite direction to the current during discharge. The following graphic evidences the recharging process. Categories of secondary battery. Secondary batteries fall into two subcategories depending on their intended applications. Cells that are utilized as energy storage devices, delivering energy on demand. Such cells are typically connected to primary power sources so as to be fully charged on demand. Examples of these types of secondary cells include emergency no-fail and standby power sources, aircraft systems, and stationary energy storage systems for load leveling. Cells that are essentially utilized as primary cells but are recharged after use rather than being discarded. Examples of these types of secondary cells primarily include portable consumer electronics and electric vehicles. Advantages and disadvantages of primary cells: lower initial cost, higher life cycle cost, dollars per kWh, disposable, replacement readily available, typically lighter and smaller, thus traditionally more suited for portable applications, longer service per charge and good charge retention, not ideally suited for heavy load or heavy discharge rate performance, not ideally suited for load leveling, emergency backup, hybrid battery, and high cost military applications, traditionally limited to specific applications. Advantages and disadvantages of secondary cells: higher initial cost, lower life cycle cost, dollars per kilowatt hour, if charging inconvenient and inexpensive. Regular maintenance is required, periodic recharging required. Replacements, while available, are not produced in the same sheer numbers as primary batteries, may need to be pre-ordered. Traditionally less suited for portable applications, although recent advances in lithium battery technology have led to the development of smaller or lighter secondary batteries. Relative to primary battery systems, traditional secondary batteries, particularly aqueous secondary batteries, exhibit inferior charge retention, superior high discharge rate performance at heavy loads. Applications of cells: internal parts may corrode and fail, or the active materials may be slowly converted to inactive forms. Coaxial cables. It is a type of cable that has an inner conductor surrounded by a tubular insulating layer surrounded by a tubular conducting shield. Many coaxial cables also have an insulating outer sheath or jacket. Coaxial cable differs from other shielded cable used for carrying lower frequency signals such as audio signals. Description: coaxial cable conducts electrical signal using an inner conductor surrounded by an insulating layer and all enclosed by a shield, typically 1 to 4 layers of woven metallic braid and metallic tape. The cable is protected by an outer insulating jacket. The advantage of coaxial design is that electric and magnetic fields are confined to the dielectric with little leakage outside the shield. Electric and magnetic fields outside the cable are largely kept from causing interference to signals inside the cable. Larger diameter cables and cables with multiple shields have less leakage. This property makes coaxial cable a good choice for carrying weak signals that cannot tolerate interference from the environment, or for higher electrical signals that must not be allowed to radiate or couple into adjacent structures or circuits. Construction: coaxial cable design choices affect physical size, frequency performance, and attenuation, power handling capabilities, flexibility, strength, and cost. The inner conductor might be solid or stranded. Stranded is more flexible. To get better high frequency performance, the inner conductor may be silver plated. Copper plated steel wire is often used as an interconductor for cable used in the cable TV industry. While many cables have a solid dielectric, many others have a foam dielectric that contains as much air or other gas as possible to reduce the losses by allowing the use of a large diameter center conductor. The insulating jacket can be made from many materials. Outdoor applications may require the jacket resist ultraviolet light, oxidation, and rodent damage. Signal propagation. These lines have low loss but also have undesirable characteristics. They cannot be bent, twisted, or otherwise shaped without changing their characteristic impedance, causing reflection of the signal back towards the source. They also cannot be buried or run along or attached to anything conductive, as the extended fields will induce currents in the nearby conductors, causing unwanted radiation and detuning of the line. Coaxial lines largely solve this problem by confining virtually all of the electromagnetic waves to the area inside the cable. Coaxial lines can therefore be bent and moderately twisted without negative effects, and they can be strapped to conductive supports without inducing unwanted currents in them. Physical parameters. Length of the cable h, outside diameter of inner conductor d, inside diameter of the shield capital D, dielectric constant, magnetic permeability. Types. The following are the types of coaxial cables: hard line, radiating, RG6, triaxial cable, twin axial cable, semi-rigid, rigid line. Color codes: yellow, composite audio; white, digital audio coaxial; orange, digital audio coaxial; green, component audio; gray, sync horizontal deflection; black, sync vertical deflection. Advantages: cheap to make, cheap to install, easy to modify, good bandwidth, great channel capacity. Disadvantages: problem with deployment architecture, noise, security risks, high costs. Coaxial cable is used as a transmission line for radio frequency signals. Its applications include feed lines connecting radio transmitters and receivers with their antennas, computer network internet connections, and distributing cable television signals. One advantage of coaxial over other types of radio transmission line is that in an ideal coaxial cable, the electromagnetic field carrying the signal exists only in the space between the inner and outer conductors. This allows coaxial cable runs to be installed next to metal objects such as gutters without the power losses that occur in other types of transmission lines. Coaxial cable also provides protection of the signal from external electromagnetic interference. Coils. An electromagnetic coil is an electrical conductor such as a wire in the shape of a coil, spiral, or helix. Electromagnetic coils are used in electrical engineering in applications where electrical currents interact with magnetic fields in devices such as inductors, electromagnets, transformers, and sensor coils. Either an electric current is passed through the wire of the coil to generate a magnetic field, or conversely, an external time-varying magnetic field through the interior of the coil generates an EMF voltage in the conductor. The direction of the magnetic field produced by a coil can be determined by the right-hand grip rule. Magnetic core. Many electromagnetic coils have a magnetic core, a piece of ferromagnetic material like iron in the center to increase the magnetic field. The current through the coil magnetizes the iron, and the field of the magnetized material adds to the field produced by the wire. This is called a ferromagnetic core or iron core coil. A ferromagnetic core can increase the magnetic field of a coil by hundreds or thousands of times over what it would be without the core. A ferrite core coil is a variety of coil with a core made of ferrite, a ferrimagnetic ceramic compound. Ferrite coils have lower losses at high frequencies. Types of coils. Coils can be classified by the frequency of the current they are designed to operate with. Direct current or DC coils or electromagnets operate with a steady direct current in their windings. Audio frequency or AF coils, inductors, or transformers operate with alternating currents in the audio frequency range less than 20 kHz. Radio frequency or RF coils, inductors, or transformers operate with alternating currents in the radio frequency range above 20 kHz. Electromagnets. Electromagnets are coils that generate a magnetic field for some external use, often to exert a mechanical force on something. Solenoid. An electromagnet in the form of a straight, hollow helix of wire. Motor and generator windings. Iron core electromagnets on the rotor or stator of electric motors and generators, which act on each other to either turn the shaft motor or generate an electric current generator. Degaussing coil. A coil used to demagnetize parts. Voice coil. A coil used in moving coil loudspeaker suspended between the poles of a magnet. When the audio signal is passed through the coil, it vibrates, moving the attached speaker cone to create sound waves. Inductors. Inductors or reactors are coils which generate a magnetic field which interacts with the coil itself to induce a back EMF which opposes changes in current through the coil. Inductors are used as circuit elements in electrical circuits to temporarily store energy or resist changes in current. Tank coil, an inductor used in a tuned circuit. Choke, an inductor used to block high frequency AC while allowing through low frequency AC. Loading coil, an inductor used to add inductance to an antenna to make it resonant or to a cable to prevent distortion of signals. Flyback transformer. Although called a transformer, this is actually an inductor which serves to store energy in switching power supplies and horizontal deflection circuits for CRT televisions and monitors. Chargeable reactor, an iron core inductor used to control AC power by varying the saturation of the core using a DC control voltage in an auxiliary winding. Inductive ballast, an inductor used in gas discharge lamp circuits such as fluorescent lamps to limit the current through the lamp. Transformers. A transformer is a device with two or more magnetically coupled windings or sections of a single winding. A time-varying current in one coil, called the primary winding, generates a magnetic field which induces a voltage in the other coil, called the secondary winding. Types. Auto transformer, a transformer with only one winding. Different portions of the winding accessed with taps act as primary and secondary windings of the transformer. Toroidal transformer, the core is in the shape of a toroid. This is a commonly used shape as it decreases the leakage flux, resulting in less electromagnetic interference. Induction coil or trembler coil, an early transformer which uses a vibrating interrupter mechanism to break the primary current so that it can operate off DC current. Ignition coil, an induction coil used in internal combustion engines to create a pulse of high voltage to fire the spark plug which initiates the fuel burning. Balun, a transformer which matches a balanced transmission line to an unbalanced one. Bifilar coil, a coil wound with two parallel, closely spaced strands. If AC currents are passed through it in the same direction, the magnetic fluxes will add. But if equal currents in opposite direction pass through the windings, the opposite fluxes will cancel, resulting in zero flux in the core. So, no voltage will be induced in a third winding on the core. Transducer coils. These are coils used to translate time-varying magnetic fields to electric signals and vice versa. Types. Sensor or pickup coils. These are used to detect external time-varying magnetic fields. Inductive sensor, a coil which senses when a magnet or iron object passes near it. Recording head, a coil which is used to create a magnetic field to write data to a magnetic storage medium such as magnetic tape or a hard disk. Conversely, it is also used to read the data in the form of changing magnetic fields in the medium. Induction heating coil, an AC coil used to heat an object by inducing eddy currents in it, a process called induction heating. Loop antenna, a coil which serves as a radio antenna to convert radio waves to electric currents. Rogowski coil, a toroidal coil used as an AC measuring device. Guitar pickup, a coil used to produce the output audio signal in an electric guitar or electric bass. Flux gate, a sensor coil used in a magnetometer. Magnetic phonograph cartridge, a sensor in a record player that uses a coil to translate vibration of a needle to an audio signal in playing vinyl phonograph records. Advantages of coils: reliable, energy efficient. Disadvantages: very fast, high magnetic flux densities. Applications: magnetic recording and data storage equipment, tape recorders, VCRs, hard disks. Scientific instruments such as MRI machines and mass spectrometers. Particle accelerators, magnetic locks, magnetic separation equipment used for separating magnetic from non-magnetic material, for example separating ferrous metal from other material in scrap. Motors and generators, transformers, relays including reed relays originally used in telephone exchanges, electric bells and buzzers, loudspeakers and earphones, actuators. Conclusion. In this chapter, the user has covered the following aspects of raw material: multimeter, component tester, open resistor damaged, optocouplers, piezoelectric transducers and potentiometers, yokes of DC motor, voltage regulators and voltage on a circuit, some types of amplifiers and burnt resistors, testing of batteries in detail, coaxial cable types and cell types, coils, disadvantages and advantages.